Hey, and welcome back to Geology. This is Miss Sparks, and today we are going to continue our discussion of plate tectonics. And so, let me get everything pulled up for us here. So, we originally started talking about the idea that once again we have the theory of continental drift, in which Alex Wagner kind of introduced the idea that the plates are shifting ever so much, and we can prove that with evidence of fossils, of landforms, of climatic change and erosional processes. And today we're going to really look at what are these plate boundaries, there's 3 of them, and how can we use what pieces of evidence that are occurring there to talk about the forces that are being applied. So once again, we're really going to focus in today on the lithosphere and the asthenosphere. Whereas the lithosphere is our main crust, we're going to break it down into 2 categories, either oceanic crust or continental crust. And then we're going to get into talking about the convection that is happening in the asthenosphere. That's going to be a driving force that kind of changes how the plates move. So do grab a sheet of paper and a pencil, and we're going to take some notes on what this actually all kind of looks like. And so once again, I've talked about there's different types of plate movements that we're going to discuss. So once again, we have continental and oceanic crust. The oceanic crust is normally heavier due to what we talked about earlier with that magnetic banding or stripping. So there is a lot of iron in our oceanic crust, which makes it heavier and more dense. Whereas our continental crust does not have as much of iron in it, so it leaves it a little bit less dense to be more floating at the top, and that's what this is kind of talking about. Plates move around on the top of the mantle like rafts. Both the oceanic and the continental crust does that. They both are moving. And so here's a picture of our different types of plates that we have. So we have our North American plate. There you can see there's the United States of America. We have the Eurasia plate that kind of wraps around there both. The Australian, the Pacific plate, the South American plate, the Caribbean, the African, and so you kind of get these ideas. And we're going to talk about what types of forces are happening. So as you can see, there's some red and blue and yellow lines. We're going to really fundamentally talk about what those plates are actually doing, which is a side view. And I actually have a picture that I'm going to really kind of give you guys and break it down a little bit further. But we are going to be looking at our 3 different types of boundaries. And this would be like a side view. So if we were to cut the earth in kind of half, we would end up being able to look at 3 different ways in which plates move, which is convergent, divergent, and transform. And as you can see, they have them up there. This is an example of our transform boundary where the plates slide past each other. And then we have our divergent boundary. And as you can see, those arrows are pulling apart. Forces are causing those plates to pull apart. And then our convergent boundary is when they're coming together. They're being forced together to do something. So once again, are 2 different types of plates. These are highly, highly important because we're going to really discuss about what's happening when we look at a plate that is more oceanic and what is happening when we look at a plate that is continental. And then if 2 of them collide, we have a resulting pattern. So oceanic plates normally are below the crust or the ocean, so they're below sea level. And once again, they are denser because they are made of that basalt type rock material that has a lot of iron and heavier elements in it. So remember, we talked about igneous mafic rock. This is our oceanic plates. Mafic, cooled very, very fast, but has very dense, heavier elements in them. Our continental plates are lighter in color. They can be igneous, sedimentary, or metamorphic, but they are normally made up of more of that felsic, that fair material, or that fair light colored minerals. And that causes the continental plates to be less dense. So remember Bowen's reaction series? the heavier elements were at the bottom, the lighter at the top. This is that same idea, that same process. So the first boundary we're going to talk about is a divergent boundary. And a divergent boundary is, I like to think, it's being divided. It's being separated out. So this is a boundary where two plates are moving apart, or they're rifting. They're being pulled apart. And this process is going to cause for new oceanic or new continental crust to be deposited. And so we have forces pulling those plates apart, and that allows for the asthenosphere to come up, solidify, cool, make younger rock. It pulls apart again, brings more magma up, it cools, solidifies, makes new rock. And so we call this one or two things. Rifting is one, which causes the seafloor to spread apart. And so you might remember we talked about the mid-oceanic ridge, which is a ridge that runs pretty much all around the Earth. The one that is most significant, that I feel like gets a lot of credit, is the mid-oceanic ridge in the Atlantic Ocean. And so it's rifting, meaning that it is way below the surface of the ocean, or below the surface of the ocean, sorry. And as it creates new crust, it pushes the older crust away and kind of builds up a rifting portion of it, if you want to think about it that way. So features that a divergent boundary is going to create is either a ridge, which is normally below sea level, or a rift, which is above sea level. And sometimes it will even cause fissure volcanoes, which are volcanoes that are normally found right along a crack along one of these rift or ridges. Iceland is a great example of two of the three of these features. Iceland sits in the Atlantic Ocean, and it sits right on top of the ridge. So once again, ridges are below. Iceland is a rift valley. It's sitting on top of this ridge, and it's slowly being pulled apart. It's part of Iceland sits on the North American plate, part of Iceland sits on the Eurasia plate, and it's being ripped apart. And as a result of that, Iceland is very volcanic. There is a lot of heat and geothermal energy due to fissures that are being moved through the area. So here is a picture of the ridge. So we have South America here, North America, Africa, and Europe. And that ridge runs all along. And there's Iceland right there, and you can see that black line runs right through it. It's another example of the ridge. It is actually very, very deep. So think almost like a trench type activity. And as you move away from it, it almost creates this mountainous-like environment. Here's another picture of Iceland. So once again, you can see this pink strip here represents the ridge. And as it comes up onto Iceland, it changes into that rift. And part of Iceland is being pulled this way, and part of Iceland is being pulled that way. And as you can see, those little pink triangles represent volcanoes that are those fissure volcanoes. Highly, highly explosive, very active all the time. The next type of boundary is our convergent boundary, and this is where two plates are being pushed together. They're colliding. So I always think of the Beatles song, Come Together. They're being pushed together. They're colliding. And so the interesting thing is, so our divergent boundaries, you can have two different types, a rift or a ridge. Whereas our convergent boundaries, we can have three different types of convergent boundaries depending on what type of plates are present. So convergent boundaries is being they're pushed together due to that convection in the asthenosphere, and as a result, we can have three different types. Our first one is what we call our oceanic continental convergent boundary. And this is when an oceanic crust comes in contact with a continental crust. So the oceanic plate collides with a less dense continental plate, meaning that oceanic plate has heavy iron in it And when they come together, the oceanic plate is heavier, so it wants to sink down. And as it does that, we call this subduction. It's being subducted, it's being pulled underneath the continental plate. And as it does this, it creates what we call a subduction zone. And that's just where the less denser plate slides under the more dense plate. So it's just kind of going down. As a result of this oceanic plate being pulled down, being subducted down, it creates earthquakes and volcanoes. And these volcanoes that sit on this oceanic continental subduction plate are highly, highly, highly explosive. This is your Mount St. Helens, your Mount Etna, your Vesuvius that completely covered up Pompeii. These volcanoes are very, very explosive because they have a lot of carbon in them from the ocean bottom because of dead organic material depositing on the ocean floor. It's brought down, kind of think of it like shaking up a Coke can, and as it explodes, it takes with it all of this energy. So oceanic continental plates, when they collide, form a subduction zone, and normally as a result, there is some type of volcanic chain that's going to be present. And so here's a picture of it. You have your lithosphere. This is our oceanic crust being subducted, pulled underneath the continental crust, the lithosphere here, lighter, stays at top. As a result, that plate gets heated up due to friction right here. It melts, creates magma, and then that fuels this volcanic chain or arc. You can see there's lots and lots of them. And so this is very, very, very common on the Pacific side of North America, as well as the Pacific side of South America. These two, that is exactly subduction zone is what is happening in the Pacific Ocean. I'm going to skip over that picture. The next plate boundary that we can have, or the next combination we can have with our convergent boundary, is what we call oceanic convergent boundary. It's when two ocean plates collide with one another. So dense oceanic plate, they collide, and as a result, since they're both really dense, they both almost subduct down, and they create a really deep impression on the ocean floor, and this is called a trench. For those of you who have seen Finding Nemo, swim through it, not over it, that is this. The trench is an area that is very, very deep. It's the deepest part of the ocean floor. We can once again find one of the deepest, or actually the deepest trench is in the Pacific Ocean, called the Marianas Trench. And what happens once again is that you have the subduction zone of two oceanic plates running into each other, and they both sink down. And as a result, it forms one of just a landform, a trench, which is a deep, deep, deep divot in the ocean floor. The Marianas Trench is actually very interesting. Only 3 people in the history of all humans have ever been to visit the Marianas Trench. There are other trenches, but Marianas is the deepest. And 2 people that visited in the early 60s were able to make it all the way down, but as they touched down on the bottom part of the trench, their windows of their submarine started to crack, so they had to be pulled up, so they weren't able to collect any data. The second person to reach the bottom of the Marianas Trench is a gentleman that you might know. His name is James Cameron. He's actually a movie producer, but also a fanatic for the ocean and nautical stuff, and so he actually funded his own mission to go down to the Marianas Trench and collect data, and he did, and he's brought back lots of evidence and data on what things are as you move down to the trench. And so here's that trench right here. We have oceanic crust, and it creates this deep trench area. So once again, kind of think of this as an idea of the Pacific Ocean. You have a trench here. Think of this as almost like your Hawaiian Islands, and then this would be like California over here. So we have a lot happening in the Pacific Ocean.